Despite its popularity, karaoke at home can still be a tedious and fragmented process. Users have to find audio removed versions of a song, which may not be available or have warped audio. They have to individually source timed lyrics, pan back and forth between their music libraries and whatever karaoke platform they're using, and buy specialized equipment in order to have even a rudimentary setup. These issues can limit the accessibility and enjoyment of karaoke for many users. There's also no way to provide feedback or gamification aspects like one might find at a karaoke room. As a result, we introduce our solution, Just Perform.
Our product aims to tackle this issue by creating one seamless karaoke experience where we allow the users to select songs from their personal Spotify libraries, which we karaokeify by passing them through a vocal removal filter and then output them through a speaker along with the user's vocals. On our web interface, we provide the users with timed lyrics to follow along with and score them based off of how well they match the lyrics and how well they move to the beat using motion data that we get from our microphone via Bluetooth.
Okay, so now we're going to walk through the software side of the web application. So when you first come in, you need to log in and it asks for permissions for different devices, access to your profile, as well as your content, and the music player, which is accessible for Spotify Premium users. After agreeing, you're logged in and it pulls up your recently played. You can see a lot of Die with a Smile, as well as your playlists. And you're able to go in and look, take a view of your playlist and play any of the songs directly from that page. We're going to go back to the home and let's say we want to sing some Billie Eilish. So you can go ahead and search and the different tracks will pop up featuring artists. You can search by song, album, anything like that. And then you can then connect. Music plays automatically. Now we're going to cue out some of my beautiful singing, but basically we display timed lyrics. We parse lyrics from Lyricify, so timed LRC files, to display lyrics as we go through. And you can see the bar updating at the bottom while our speech-to-text algorithm runs. We use threads and Asyncio and some database background stuff that we update to sync separate threads to our backend and then use a JSON endpoint with URL with periodic polling to update the scores in real time. This is just using the audio scoring, but both audio and motion scoring come through. We use the results from the real-time scoring to then generate a score at the end. So in this one, I tried to sing mostly right, but with a couple little blips, and you can see the scores
You can go
pop through
in
at the end.
and look at.
There are three main components to Just Perform system hardware. The first is our vocal removal circuit. This takes the left and right channels from our stereo audio and is able to largely attenuate the primary vocals. The second is our microphone's preamp, and the third is the mix that takes our microphone signal and our vocal remove signal and outputs the final combination to our speaker. The first and largest component is our vocal removal circuit. Here we take the analog signal from the left and right channels of our laptop output and feed it first into a high-pass filter. This simple RC filter removes unwanted DC offset, which can bring in additional noise and artifacts. Next, we see our first op-amp circuits, one for each channel input. These op-amps are set up as voltage followers, which prevents signal degradation and distortion by providing a high impedance to measure the voltage accurately. Coming out of the voltage followers, the signals enter the subtraction circuit. This subtraction circuit exploits a frequent trend in stereo music, where producers and artists spread the instrumental across both channels, so that different instruments appear in different spatial locations. However, often we find the lead vocalist centered in space, and to achieve this, producers include the same vocal signal on both channels. This means that we can invert one of the channels, which has no audible effect, and sum them together. By doing this, we achieve our desired attenuation and cancel these signals out. And all put together, our hardware sounds like this. So as you can see, there is still a remaining vocal track in the background, a small remnant, but it is severely attenuated, and you can see that in comparison to the instrumental in a second, and also those backing vocals that come in on the whoos. So there you have it. The next circuit is our microphone preamp. Since we're using a wired dynamic mic, we receive our signal at an extremely low voltage. This can be in the region of a couple millivolts or hundreds of millivolts. We must raise this to what is called line level, around a volt or two. This is about the volume that we're getting our signal from the laptop. This circuit amplifies the signal while including coupling capacitors to reduce annoying whining, buzz, and other distortions you'll find with the mic. Finally, both of these signals travel to our summation circuit. The summation circuit gives us the ability to decide the gain for both signals independently, which is helpful in balancing the sound. Here, we overlaid the microphone signal over our vocal remove track and sent it off to the speaker. Our speaker, though, is an active speaker, which means that it's able to amplify on its own with a volume dial, and meant that we did not need to amplify any further after this, and were able to keep the individual gains at this part around 1 because of our preamplification of the microphone signal to around the same level as the vocal remove track. Finally, this output is sent to both left and right channels of our speaker, which plays the final karaoke.
To collect motion data from our users, we use an MPU 6050 sensor to detect their acceleration values. An ESP32 is used to read the X, Y, and Z values and format them into UTF-8 encoded string. Additionally, it sets up a Bluetooth low-energy server with a characteristic that allows notification and updates it every 100 milliseconds to transmit the values to the web app. On the receiving end, we have a Python script that uses the Bleak library to connect to the ESP32's BLE service and subscribe to notifications from the accelerometer characteristic. When new data is received, the script decodes the string, extracts the X, Y, and Z values, and performs a magnitude comparison between the acceleration vector of the current data and that of the previous data to detect significant changes in motion. Additionally, the script tracks a rhythmic beat, continuously updating the timestamp of the last beat. This timestamp is compared to the timestamps of the detected motion changes to generate a score from 0 to 1 based off of how close they are to each other.
So for our testing and verification, the first thing we looked at was our left-right subtraction latency and accuracy. The latency beat the requirement significantly, as it is completely unnoticeable. It happens completely in real time. The accuracy, though, was quite variable, but most of the time it fell around a quarter of the original signal. So some songs went down very low, but all of them had some vocal remnant as we expected. For our speech-to-text accuracy, we got an accuracy of around 80%, which is up from 70% at our final presentation. With a couple of tweaks to the amount of time it waits for you to stop talking, we were able to get it to more quickly react to ends of lines and get you your score back quicker and more accurately. However, we did find that it struggles in noisy environments, which unfortunately are going to be inevitable in our karaoke situation. Our system boot latency is extremely fast, starting up in around a second, so the entire web app UI and connection to Spotify is super quick and gets started immediately. Our change in direction algorithm accuracy, which powers our scoring system, was able to accurately report users' movements with an average deviation of 7%, which beat our standard of 10%. And finally, the feedback on both our audio and motion scoring is extremely quick and happens in real time. All of this information gets back to the user in about a second and is displayed on the screen. So those were our testing metrics, and this has been Just Perform. A big thank you to Professor Sullivan and our TA Junjet for all the help, and we hope you guys enjoy our demo and liked our project. Yeah, thank you very much.